In the previous video, we introduced the gradient of a function and its notation, but we didn't talk about what it actually represents. Since the gradient of a function is a vector, we know that it is a quantity that has both a magnitude and a direction. We're going to start by looking at its direction. We arrived at our formula for the directional derivative by thinking about the algebraic formulation of the dot product. But since we're trying to understand the geometry of the gradient, it makes sense for us to think about this dot product using a geometric formula. Remember that u is a unit vector, so its length is 1. The angle theta is the angle between the gradient and the unit vector. By substituting this information into the geometric formula for the dot product, we get this result. We are going to think through the case where the gradient is perpendicular to u. There are a lot of little steps in the logic, so you may need to watch this a couple times and pause it to make sure you really understand the steps. If theta is pi over 2, then the dot product is 0. That dot product represents the directional derivative, so the directional derivative is 0. The directional derivative tells us the slope of f in the direction of u, and since the slope is 0, the function is not changing in that direction. If we move along a path where f is constant, we are moving along a level curve of f, and so u must be tangent to the level curve of f at that point. But since u is perpendicular to the gradient of f, we know that the gradient of f is perpendicular to the level curve at that point. In fact, we can push this even further. Now let's suppose that u and the gradient point in the same direction. Then theta is equal to 0, and the cosine function is at its maximal value. And this means that the dot product is at its maximal value, so the directional derivative is at its maximal value. Another way of saying this is that when u is parallel to the gradient, the directional derivative is as large as possible. This means that the gradient is pointing in the direction that gives us the steepest positive slope. If u and the gradient are pointing in opposite directions, then the dot product is at its smallest value, and this means that the direction opposite the gradient is the direction of steepest descent. Again, the logic here requires a lot of little pieces coming together, and so it's going to feel like it went quickly. This is a situation where you need to set aside some time and think through each step to make sure you understand it. This is the sort of mental exercise that really helps you to become a more careful thinker if you do it, and that skill pays off in ways that go well beyond this class. The book talks about applications of the gradient using the context of simulating heat-seeking missiles by measuring the local heat gradient. You're encouraged to read about that in the book. I'm going to use a couple different ideas. Let's think about the consequences of the gradient pointing in the direction of steepest descent. What this means is that if we imagine the function as a surface and place the ball somewhere along it, the ball will naturally roll downhill in the direction opposite the gradient. And this idea can be used as a basis for modeling how water would run down the side of a hill. And that's one application of the concept of the gradient. Another application comes from the world of data science. A common task in mathematical modeling is finding the equation of a line that is the best fit for a bunch of points. Usually these points aren't in a perfect line, which means that any line that we draw is going to have some error associated with it. Intuitively, some lines will have larger errors than others. The goal is to find the line that minimizes the error. In other words, the error is a multivariable function and we're trying to minimize it. This is often an extremely complicated function, so that we don't have a good analytical formula to use our normal optimization techniques from calculus. And so we need a different tool. That tool is known as gradient descent, and it works in a similar way as the ball rolling downhill example. We can try to find our way to the minimum value by estimating the negative gradient of the function relative to our current input values, and use that to give us a new set of parameters. And by repeating this, we can hope to converge to the values that give us the smallest error. So far, we've talked about the direction of the gradient, but what about its length? There's not nearly as much to say about this, but we also can't ignore it. Let's return to the directional derivative equation we were analyzing earlier. When u is parallel to the gradient, theta is equal to 0, and this expression simplifies to just the length of the gradient. We have already seen that the gradient points in the direction of steepest ascent. But with this additional observation, it means that the length of the gradient is the slope in that direction. In other words, the length of the gradient gives the maximum rate of change of the function from that location. And this is another way to interpret the meaning of the geometric properties of the gradient. The gradient of a function and the del operator are important tools for multivariable calculus. We're going to see a number of different applications of it over the next couple sections.